Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about the likelihood for the simple linear regression model. Let's begin. So, the model that we're going to use to set up the likelihood function and to analyze the simple linear regression model from a Bayesian perspective is going to be what we're going to be calling the alternative simple linear regression model. Okay, so let me write that down for you. Okay, so the alternative simple linear regression model. Okay, so what we're going to be doing is we're going to be mathematically modeling our response variable, the variable that we want to predict, with the following mathematical expression. Okay, alpha sub x bar, that's the notation that the authors of our textbook use, right? Plus beta is slope times xi minus x bar plus epsilon I. Epsilon I represents a random fluctuation, and we are going to make a few assumptions about the probabilistic behavior of that random fluctuation. We are going to be assuming that it's normal with mean 0 and variance sigma squared. Furthermore, we're going to assume that sigma squared is known, right? We assume that sigma squared is known. Okay, something more. We're going to be assuming that the epsilon i's, okay, the errors, the random fluctuations for each individual yi are independent. Okay, so epsilon i's are independent, and as we said, we assume that sigma squared is known. Okay, now let's try and construct the likelihood function for this model. Okay, so likelihood for a single observation. Okay, so if we think about the likelihood, right, as a function of a function of the unknown parameters, right, but for particular values of those parameters, right? So what we're going to have is something like this. So f of yi, right, given particular values of alpha, x bar, and beta, because we're assuming that sigma squared is known, right? Given the assumptions, note that if we have the values of alpha and beta, and the xi's are also known values because those are the values for the predictors, right? So this guy, the yi, is a sum of constant plus a random variable that is normal, so the distribution of the yi's is going to be normal. The mean is going to be this guy, and the variance is going to be the variance of epsilon I. Make sense? So what we have, as we said, is that the yi's have a normal distribution. This is going to be the mean, and the variance is going to be the variance of the epsilon I, sigma squared, right? So if you will, we could write that down like this, that the expected value of yi, right, given that we have these guys, or not words, for given values of alpha x bar and beta x bar, and beta, sorry, it's just going to be this, right, because the expected value of the epsilon's 0, right, and the variance of the yi's, if we're doing this for fixed values of alpha x bar and beta, then these would be constants, and then we would have only the variance of epsilon I, then we would have sigma squared. Okay? Okay. So, we know that the PDF of a normal looks something like this. 1 over the square root of 2 pi times sigma e, and we're going to have e to the power negative 1 divided by 2 times sigma squared times yi minus its mean, right? And let me write it down like this instead. Okay, let me use curly brackets for this. Let me get rid of this, and let me rewrite yi, because we have to be very careful with these. We don't want to make any sort of mistakes. So minus the expected value, and this is the expected value given particular values for alpha x bar and beta. Okay, the whole thing squared. Here, oh, I don't know why it moved. There, squared. Okay, we don't want to have anything here. Okay. Okay. So now let's just keep going. That's the likelihood for a single observation, and then this is going to be for values between negative infinity and infinity. Okay? There we are. Okay. So now let's find the likelihood for a sample. So now, instead of having one single observation, one y, we observed several, right? y1, y2, up to yn. So what we know is that since the epsilons are independent, okay, the yi's inherit that independence. The yi's are also independent. And we know that the likelihood of a sample of independent observations is just the product of the individual likelihoods. Okay? So let's multiply those guys. So it's going to be the likelihood of first observation times, and then we are going to have n of those terms, right? The other one would be something like this, but with an n in it, right? Times something like this, nth observation. Okay? Agreed? Okay. So now, we are assuming that sigma squared is known, right? And we have particular values of alpha, x bar, and beta. Okay? So the thing is, sigma squared is known, and then what we're going to be doing is using the proportionality symbol, and we're going to ignore the terms that don't involve the parameters alpha, x bar, and beta. Okay, so these constants we're going to ignore, and then what we have is just the product of those exponentials. Okay, just these guys. Okay. Okay. Now, let me use the following notation for e to the something, right? I'm going to be using that notation for e to the power something, okay? So we have a product of n exponentials. So we know that all we have to do is add the exponents, okay? So that's what we're going to be doing next. Note that -1 divided by 2 times sigma squared is a common factor, so let's treat it as such. And then we are going to have the sum of terms that look like this, okay? So summation I goes from 1 to n of this, make sense? Yeah? But we have yi's instead of this. Okay? And this is a common factor, so let me pull it out. Okay? Agreed? Okay. So next step. What we're going to be doing here is doing a little bit of algebra with that exponent. The first thing that we're going to do is we are going to add a 0. Okay? So we have minus y bar plus y bar. Okay, now let me put these guys together. And okay, let's be careful here. Let me see. Oh, yeah. I have here, what I wanted to do was add a 0. So I had yi minus y bar plus y bar minus. This is a minus, what I need to have here. Okay? Okay, good. Okay. So now, let's do the algebra. Okay, we're going to treat this guy as one term, so we want to square this plus this. We're going to treat this as a second term. Okay, so here we go. So it's going to be summation of yi minus y bar squared, okay, plus 2 times cross product between yi minus y bar times this. We're considering this guy as a single term, right? Okay, so first one squared, 2 times the cross product between this and this, okay, and plus this guy here squared. Okay, the whole thing squared. Makes sense? And then we don't need this one anymore. It's done. Okay, taken care of. We good? So we have this one squared, 2 times the cross product between these two, and we have the second one squared. Okay. Okay. Now let's break down that huge sum into just 3 sums. Okay. So we have 3 summations. So we have first one is just the first term. So bless you. So okay. So next what we have is 2 times, right? That's going to be a common factor, and we're going to have this guy, right? Summation of let me copy paste it. Okay. There we are. Okay. This one here we can pull out. Okay, so next one, the last one, it's going to be the sum of that squared. Okay, so here we go. Last one. So the last term looks like this. Okay. Are we good? So the first one we're going to leave untouched. Okay? But we have to play around with the second one and the third one. Okay? Okay. So, let's talk about this one first. We're going to try and simplify that one. So, this is the same as this. yi minus y bar times just y bar. That's the first one. And then we're going to have minus the summation of yi minus y bar times alpha x bar, right? And then we're going to have minus as well, right? Because we have minus times plus, right? We're going to have minus summation of beta times xi x bar times yi minus y bar. There we are, right? Okay. So, we are almost there for that one, anyway. So note that this is a common factor. We can pull it out here, right? So, y bar is also a common factor. We can pull it out. There we are. Okay. Now, let's pay attention to this guy, yi minus y bar. So note that the summation of yi minus y bar is going to be 0, right? So, because then it would be summation of yi's minus n times y bar, but n times y bar is the same as summation of yi's, so that's 0. And we did something similar with xi's and x bar in another video, right? When we showed the equivalency between the formula for the slope for the original form of the least squares regression line and the alternative form of the least squares regression line. Okay, so let me just point that out, since this is equal to 0, this guy goes away, this guy goes away as well, and then we are only left with this term here. Okay, so this one we said we were going to leave untouched. This one we have already dealt with, right? This one now, it looks so much better. This is just going to be negative summation of beta times xi minus, well, xi minus x bar, yi minus y bar, right? And we can actually, you know, factor this one out just like that. Okay, so now this one looks nicer, right? And by the way, we're going to introduce the following notation. if we have that sort of cross product, xi minus x bar, yi minus y bar, we're going to use ss sub xy to refer to that cross product. Okay? Okay. So now the second term looks nicer. Let's talk about this one here. Okay? Let's try and simplify that one, and then we will be done with that part. Okay, and that's going to be very important for obtaining the likelihood. Okay, so here we go. Again, let's do the algebra here. Okay, so in this case, once you multiply by -1 here, what you end up with is negative alpha x bar and negative beta times xi minus x bar. Okay, so now let's treat these two guys as one single term, and this one is going to be a second term. Okay, and now let's do the algebra. Let's expand. So it's going to be the square of this guy, minus, right? We're going to have minus 2 times the cross product between y bar minus alpha x bar and this guy. So we're going to have a beta xi minus x bar. Okay? Okay. And finally, we are going to have plus beta squared times xi minus x bar squared. Okay? Okay. Now, instead of having a big sum, we're going to have 3 smaller sums. Okay? So we're going to have the first one. It's just the first term. Right? Plus, now we have the second term here. Plus, we have the last term. Okay, wow, almost there. Anyway, this is a common factor, right? Can you see that? Minus 2 times beta y bar minus alpha x bar, and that doesn't depend on I. So we just pull it out. Okay? Summation of xi's minus x bar. Okay? Okay. Now, this one, beta squared, is also a common factor. Let's pull it out. Okay, and okay, so now this one here, note that this is just summation from I going from 1 to n of y bar minus alpha x bar squared, right? So this is the same as just plain n times y bar minus alpha x bar squared, right? So let's simplify that one. So this is just n times this guy. Now, summation of xi's minus x bar, that's going to be 0. Okay? So let's get rid of it. And that's it, right? So after our hard work, we're going to be able to simplify the expression that we had for the likelihood. Okay? So this is what we had at first, right? Let me remind you. We had that the likelihood for the sample was, the exponential, an exponential to the power -1 divided by 2 times sigma squared times this, right? Then we expanded that, but we did this trick. We added a 0, so we have y bar plus y bar minus y bar, that's a 0, right? So, and then we did the algebra, and we had these 3 terms, right? This one, and this one, right? Okay, so now let's simplify the expression that we have here. So the first one, no problem, we're going to leave that as is, but the second one now looks so much better, right? The second one is going to be this. So what we have here is, instead of this guy, so we have minus 2 times beta times SS xy. Okay, now this one here we said is equivalent, right? This one here is equivalent to n times y bar minus alpha x bar squared plus beta squared times that summation. Okay, perfect. Okay, so we're making progress. We're almost there. So the likelihood of our sample using this, right, now looks like this. So instead of that summation that we have here, let's have those 3 terms. Here we substitute these. Okay. Okay. Makes sense? So we have the exponential to the power -1 divided by 2 times sigma squared times these guys, right? Makes sense? Okay. So now, just as we had this notation for the summation of xi minus x bar times yi minus y bar as ssxy, right? We're going to have similar notation for the first summation that we have in that expression, okay? So let me copy paste this in another one. If we have problems, so let me open a new document here. So now this guy here is going to be what we're going to be referring to as SS sub y, okay? So is this guy here. Instead of writing y, the summation of yi minus y bar squared, right? What we're going to be writing is SSY. Okay? Makes sense? Okay. So the likelihood of our sample looks like that. Okay, now it doesn't look so scary. The other one, the other change, as you can imagine, that we're going to include here is that just like we change summation of yi's minus y bar squared for SSY, we're going to substitute this one, right? We're going to change it for SSX, right? Okay? Sum of squares of the x's. Okay? Okay. So now we're making progress. Well, so now note that we have terms that have to do with alpha, only one, and terms that have to do with beta, and one that doesn't have to do with any of them. So let me just rewrite this as follows. Okay, I'm going to rewrite this as the product of two exponentials. Okay, the following two exponentials. This one here and this one here. You guys agree that they're the same, right? So this is a common factor, right? So we have it in both, and then when you multiply two exponentials, all you have to do is add the exponents. So these two expressions are equivalent. Make sense? Okay. So we're almost there. Okay? Now, let's pay attention to the first term. Okay? The one that has to do with beta. Okay? Let me talk about this guy here. So what we would like to do there, and let me tell you what the plan is. So we know that the kernel of a normal random variable looks like e to the negative 1 divided by 2 times sigma squared times some variable minus its mean, right? So we almost have that for beta, and that's one of our parameters, right? So it would be great if we could make the kernel of a normal appear in terms of beta, right? So what we're going to be doing next is we're going to try and complete a square here to make that kernel of a normal appear for beta, right? And then we're going to be doing something similar for alpha. Okay, makes sense? But for alpha, you'll see it's going to be really simple. So that's why we're going to be doing it first with beta. So first, what we're going to be doing is we're going to be factoring out that SXX. Okay? So here we go. So let's factor out that SXX. Okay? But by doing that, right, we have to divide this one by SXX, right? We divide by SXX, this one as well. Make sense? Okay. And then what we do is we just square, right? It would be nice if we had the square, right? So we have beta square, we have this, we would like to have this term squared, and we don't have it. But the thing is that we could add a 0, right? So we could make it appear. That's what we're going to be doing next. So let's add and subtract that 0. And let me just make these guys, reorder these guys, right? Beta minus 2 times beta, and that, let me do plus, and what we need is the square of that guy. So we have a plus, then we have a minus as well. And this one we already have. Okay, is this guy, right? So this is the 0 that we added. Okay? But now this is just the same as beta minus SSXY divided by SSX squared, right? So let me just write that down here. So this is the same as, let me write it down like this, beta minus SSXY divided by SSX, the whole thing squared, right? Instead of having these 3 terms. Make sense, right? Okay, so now the thing is, we have that first exponential. We could rewrite it like that, right? Okay, so let me rewrite the first exponential as the product of, well, we're going to have these, right, instead, right, in the exponent. So it's going to be the product of 2 exponentials. Okay, so let's do that here. We're almost there, so close. We almost have the likelihood that we want. Okay, so instead of that, now we have this. Okay, makes sense? And we had this exponential. Now let me just say something about that exponential. Note that that n is a common factor. So let me put it here, right? Okay. Okay. So what we're going to be doing next is these these terms, right? That would be the same as the product of the following two exponentials. Okay. So we would have this. Let me copy paste this, and then I'm going to keep only. So first I'm going to keep only, right, this one here, the one with betas, and I'm going to get rid of this one here, right, and for the other one I'm just going to keep these, right? So another way of writing that would be this. Okay, so anyway, what I did is I rewrote that exponential as the product of two exponentials, right? That's fair. That's fair game. Okay, and we have the other one, the one with alpha, the one that we had from before. Now note something, the one in the middle, we are assuming that sigma squared is known, so that can be absorbed in these guys. The x's are known, the y's are observed, so these are constant with respect to alpha and beta, right? So these can be absorbed by the proportionality symbol. Okay, so what we have is this, that this is just a constant with respect to alpha and beta, okay? So now this is a common factor, right? Let me pull it out here. And I want you to take a close look at this guy. You go, oh, I know that the kernel for normal is -1 divided by 2 times sigma squared, right? E to the -1 divided by 2 times sigma squared times the variable, in this case beta, minus its mean squared, right? Here, e to the -1 divided by 2 times sigma squared to the power, in this case, right, we know that y bar minus alpha x bar, that's the same as doing this. Y bar minus alpha squared, oops, is the same as alpha minus y bar squared, right? Okay, so to be super specific, right, so we can clearly see that now we have the product of two normals. Let me do this. This is the same as sigma squared divided by SSX, right? Agreed? and this guy here we can divide by n, right? So these two expressions are equivalent, right? So what we have is that the likelihood for beta and alpha, right, is proportional to the product of two normals, two independent normals, one for beta, one for alpha, right? And note also that it turns out that B, right, this guy here, this is what we had for B, right? Recall when we talked about you know, the estimators, the least squares estimators for beta and alpha. Recall that B could be written like this, right? The summation of xi's minus x bar times yi minus y bar divided by the summation of xy's minus x bar squared. Right? And this is exactly what we have here, right? SS xy divided by SSX. And also remember that the estimator that we had when we used the alternative form of the least squares regression, right, was just y bar. Make sense? Okay. So let's summarize what we did thus far, and this is going to be really important for us. This guy here, this expression that we have here, is the likelihood for a sample, right, for our linear regression model. But it turns out that it happens to be the product of two likelihoods, independent, one for beta, one for alpha. And this is the likelihood of a normal, right, with mean SSXY divided by SSX and variance sigma squared divided by SSX, right? And this is the likelihood for a normal with mean y bar and variance sigma squared divided by n. And since these likelihoods are independent, then we are going to propose independent priors for beta and alpha, and it's going to be so much easier to do this, to analyze this model from a Bayesian perspective. Okay? So, yeah, I know that it was a lot of hard work, right? It was time consuming, but this is going to be really important. So in another video, we're going to use this likelihood for the alternative simple linear regression model to analyze data for a simple linear regression model using a Bayesian approach. Okay, well, thank you so much for watching. Please take care and keep working hard. See you next time. Bye.